Okay, we're going to take a look at some examples of syntheses that require multiple steps. And specifically, we're going to look at what's required to move a leaving group or to move a pi bond. So if we look at these two examples, in this first case, right, I'm moving the bromine from this position to this position. And we didn't learn any one-step reactions that can do that. Same thing down here. To move this pi bond from here to here, we didn't learn any one-step reactions that can move a pi bond. However, if we combine the elimination and addition reactions that we've learned, that will allow us to move both leaving groups and pi bonds. For example, if I start with this substrate and I do an elimination, I can put a double bond here. I can then do an addition that moves the bromine. I could then do another elimination, and the addition elimination step resulted in the moving of the pi bond. And I can do another addition and put the bromine in a different spot. So by carefully choosing our reagents to achieve Markovnikov or anti-Markovnikov addition or the Zaitsev or the Hofmann product, we can effectively move around these leaving groups or pi bonds. Now we need to be careful when we pick our reagents, right? We need to determine which product we need. Do we want the double bond to go to the more substituted carbon or the less substituted carbon in the case of elimination reactions? And so if I use a strong base that's not bulky, I can get the Zaitsev product. If I use a strong base that is bulky, then I can get the Hofmann product. Similarly, for addition reactions, we need to consider whether we desire Markovnikov or anti-Markovnikov addition. If I want to put the bromine here, I'll do Markovnikov addition, and so I can just add HBr. If I want the anti-Markovnikov product, right, then I want to use HBr in the presence of peroxides. Okay, let's look at a couple examples. So we're asked to propose a synthesis to convert this compound into this compound. And so you can see we've moved the OH from here to here. Right, so this is not a simple substitution, elimination, or addition, and so we need to combine two processes. If I start with this compound and do an elimination, I can put the double bond here. I can then do an addition that adds the OH here, but I have to pick my reagents properly so that I get the right product at each stage. So I picked this example specifically because it involves a concept that I didn't really cover in my Chapter 7 videos, and I think that was a mistake. So I want to correct that mistake here by covering this topic in this example. So in the section on other leaving groups besides halogens, we did talk about OH and the fact that it's not a good leaving group. Now, one thing that we said we could do was, in the presence of a strong base, we could protonate this and turn this into, OH2+, which is then a good leaving group. Now, that won't work in this case for a number of reasons. First of all, that's going to cause an SN1 mechanism, and that's I can't control. So we're always going to get the Zaitsev product, and so we would get our double bond here, right, when we want our double bond to be here. The other problem is I can't have a strong acid present when I try to add the strong base, because they're just going to neutralize each other and they're not going to react. And so an alternate way to turn OH into a good leaving group is to turn it into a tosylate. And so if I react it with this tosylate chloride in the solvent pyridine, then I can convert the OH into a tosylate, and this is now a good leaving group where the OH was not. So this is a very useful step for converting an OH into a good leaving group. So then, because I want the double bond here, I want the Hofmann product, not the Zaitsev product, we're going to use a bulky base. And so our first two steps, right, so we're going to convert the OH into a good leaving group. Then we can achieve the elimination by using a bulky base to get the less substituted alkene. Okay, and then once we've produced the alkene, we want to put the OH here. So we need an anti-Markovnikov addition of H and OH, and so we can achieve that with hydroboration oxidation. And so these are the synthetic steps that we would use to convert this compound into this compound. Okay, here's another example. And so effectively, we're moving the double bond from here to here. Now, we're actually moving the double bond 2 spaces, and that's okay, but it's probably going to require a couple of combined addition and elimination steps, because one addition and elimination could move the double bond here, but I need to move it over 2 spaces. So we're probably going to go through an alkene like this as one of our intermediates. So the first thing I need to do to move the double bond is do an addition reaction. And so if I'm trying to get the double bond from here to here, right, then I need to end up with my halogen on this position. And so I need a Markovnikov addition. And so to do that, I can just add HBr. So if I add HBr, I'll get Markovnikov addition, and the bromine will go there. Now, for the next step, I need to go to this alkene. And this is the more substituted alkene, so we want the Zaitsev product. And so I can do that by reacting this with a strong base. So I'm going to go with NaOH. I don't want a bulky base because that would give me the Hoffman product, the less substituted alkene. I just go back to my starting position. So I want to use a non-bulky base to get the Zaitsev product. Okay, so we're a little bit closer to our destination, right? We've got to get the double bond from here to here. So now I want to add a halogen to this carbon. Now this is going to be anti-Markovnikov addition, right? Because normally if I just added HBr to this, then the bromine would go here. So to get the bromine to go here, I need to do anti-Markovnikov addition. So if I do HBr in the presence of a peroxide, I can get the anti-Markovnikov addition. So the bromine is going to go there. And so with one more step of an elimination, I think I can get to our final product. But in this case, I need the Hoffman product, right? So normally it would prefer, when I do the elimination, to get the more substituted alkene. So to get the Hoffman product, I need to use a bulky base. And so for that, I'm going to use the tert butoxy. And so that should achieve the final step of my synthesis. Okay, one more example. In this case, I'm starting with a bromine, and then I'm moving the leaving group to a new position, and I'm changing the identity of the leaving group. But there's no real problem with this, right? Once I form the alkene, right, then I can do whatever addition I want. And so we need to get the double bond here, and then I can add or do the proper addition to get an OH instead of a bromine. So if I want the double bond to be here instead of here, I need the Hoffman product, so I need to use a bulky base. So the bulky base we usually choose is the tert butoxy. So that will give me the less substituted alkene. And then to get to the final product, I need the anti-Markovnikov addition of an OH. And so I can do that with hydroboration and oxidation. So if I use BH3 and THF, and then hydrogen peroxide and sodium hydroxide, I can get the anti-Markovnikov addition of water, and that will result in my final product.